So welcome everyone. So in today's lecture we will continue our discussion on the bias variance decomposition. So last time we saw that with the goal of minimizing the risk function when we start building algorithms, the errors that we encounter can be decomposed into two parts. Right? The one was called the bias, the other was called the variance. Bias refers to, or rather bias measures or quantifies what is the deviation of the classifier or the hypothesis that the algorithm has yielded us from the true minimizer of the risk, underlying risk. That is the bias term. And variance quantifies how sensitive is our hypothesis to a particular choice that we have made of the data set, or how sensitive it is to changes in the data set is what variance captures. And a good classifier is the one that minimizes the risk, right? And to minimize the risk you want both the components of the risk, which is the bias and the variance, to be simultaneously minimized. Okay, a good hypothesis is one that would minimize both the bias and the variance simultaneously. However, as we discussed in the previous lecture, when you have smaller models, limited parameter models and limited amounts of data, typically there would be a tension or a trade-off between bias and variance, in the sense that if you try to minimize the variance, the bias would increase and vice versa. Now why would this happen is the question. Okay, now this happens because of something called manifold hypothesis. We will discuss more about this in the generative modeling course, but roughly the idea is the following, right? So think about this. So we are dealing with data, right, which are vectors in d-dimensional real space, right? Now let us say that we are looking at images, for instance, and let us say that we are looking at binary images, okay, the images that will only have 1 or 0 as their pixels, grayscale images, okay, they can be looked into as binary images. Now suppose you are looking at, let us say, a 100 by 100 image, then all the images or the data points that you get are vectors in 10,000 dimensional space, a 10,000 dimensional space which has binary values into it, right? That is what it is. So it is an image would be a point in this particular space, right? Now let us say that we do this experiment where we assume each of the pixels, each of these grids of this image as an independent Bernoulli random variable, okay, then we will toss a coin with probability p. Now if that coin turns out to be head, then we will fill that pixel with 1, and if it turns out to be tail, then we will fill that pixel with value 0, okay. Now if you toss 10,000 times, you get one image, do you understand, right? So basically it is 10,000 independent Bernoulli trials is what you do to get one image. Now tell me, what are the odds that by doing this experiment you will end up getting a meaningful data set like MNIST? What is it? It is extremely low. It is a non-zero probability, but it is extremely low. But in fact, this is also known as the typewriter monkey problem, where the thing is, you make a monkey sit in front of it. Do you know what typewriter is, Gen Z people? Okay, there used to be a device called typewriter, right, where people used to typeset and print and all that. So yeah, so you make a, or maybe the newer version of it is you make a monkey sit in front of a keyboard, right? And see, today with all these voice based models coming in, so maybe 2-3 years keyboard also will become obsolete, who knows. Anyway, so you make a monkey sit in front of a typewriter or a keyboard and make it randomly press the keys. The question is, what are the odds that it comes up with Hamlet, Shakespeare's work? What are the odds? It is a non-zero probability, but it is a very less number, right? Now think about it, right? P, which is a Bernoulli, which is the probability of success of a Bernoulli trial, is by definition less than 1, and you multiply that 10,000 times, it becomes very, very less, no matter how higher the probability is. Now what does this tell you? This tells you that the MNIST data set that we get, right, occupies a very, very small space in this ambient 10,000 dimensional space. Do you see what I am saying? So this is called manifold hypothesis, okay, which says that most of the data that we get in practice occupies a tiny little manifold, as it is called. I mean, manifold is a topological object, I will not define that. Think of it like a subspace, okay. It is not a subspace, but think of it like a subspace, very small tiny subspace in the ambient space. So data that we deal with always occupies a very small subspace or a manifold in the ambient space that we are operating with, okay. Now what does it do? What does that has to do with bias variance decomposition is the question. Now if you are trying to build a regressor or a classifier on this particular data, what are you trying to do? You are trying to partition this manifold. See, what is a classifier at the end of the day? If you are looking at a binary classifier, all that you are doing is it's a set partition function, right? I mean, given 1000 data points, it will group one set into one particular class, the other set into it's basically creating subsets of the support set of your random variable. That is what you are trying to do as a classifier. Now if you were to do that in an ambient space, okay, over a data set that occupies very small tiny manifold, then what happens is that if you want to explain the given data set, then you will tend to end up overfitting it, because you want to explain everything, right. So since it occupies extremely tiny space, if you were to build something, partition this very tiny space in your ambient space, then you will have to build something that is extremely specific and confined to that tiny manifold. That is why the problems, unless you have large amounts of points in your data set that would occupy much more space in the ambient space, it is very hard to build classifiers that would have both bias and variance extremely low. So now suppose you end up, let us say that you have a tiny manifold that you are dealing with and you want to explain the data that you are given. I mean, that is the only thing that we can do in ERM, and while doing so you build a classifier that has very high bias, which is the overfitting region. If you get there, obviously if you change that manifold, if you move that manifold from one point to the other, which is your test data set, you are going to do very badly, right. So variance will be very large in that kind of a case. So if you end up not making the model have a large variance, then you will not even explain that small manifold that you are given with, which is the underfitting regime. So that is why in practice, because of this fact that data occupies an extremely small tiny manifold in the ambient space and you are trying to explain your data with very small number of samples, you will always end up, if you want to optimize for bias or reduce the bias, then you will end up increasing the variance and vice versa, okay. Now when does the scenario change? The scenario changes if you have a very large amount of data, right. So the tiny space that it is occupying now becomes extremely large. So now let us go back to our typewriter monkey problem, right. Instead of making it type Hamlet, if you ask me what are the odds that it will type one word that makes sense, the odd will go up, right. So that is expanding your data space. Now that is why today's ML methods are effective, because the kind of amounts of data that we are dealing with are so large, right, that you can hope to reduce the bias and variance, both of them simultaneously. But typically that does not happen, and we saw that behavior in the previous class, right. This is the usual bias variance curve, right, where as you increase the model capacity till a point, I mean the error or the accuracy on the training data keeps decreasing, while the accuracy on the unseen data keeps decreasing till a point and then starts increasing. You will have to see this behavior, right. Okay. So given this background, the question now is, what is the best way to operate in a pragmatic approach? So I told you the last class itself that typically what is done is that you start with an over parameterized model, right, overfit the data and then increase the bias, push the model back, so that this is the ideal operating point, and to get there you start with an over parameterized model and increase the bias of the model, okay. Now any technique that is used to increase the bias of a hypothesis is referred to as regularization. That is why I had to give such a long prologue today. See, regularization refers to techniques to increase the model bias. Okay, there are multiple ways to do this. Starting from penalizing your empirical risk, the loss function, or re- restricting the hypothesis class to a particular functional form is also a way to increase the bias. So remember what we said in the earlier classes. The moment you restrict your hypothesis to a particular class of functions, it amounts to putting a restriction on the class conditional density, right? Any choice that you make on your class conditional density is increasing bias. Now all models are implicitly biased. See, unless they are they are, even if they are universal approximators, the moment you make an architectural choice or a design choice at a hyperparameter level, then you are imposing a bias on the model. So there is no unbiased model. All models are biased. Now the question is, by regularizing you can steer this bias, you can actually increase the bias, right? So there are multiple ways to do that. As I said, any architectural choice is a bias. That's why I keep saying that any innovation that has happened in coming up with newer architecture is actually imposing some sort of a bias on the model, including transformers. We'll see that as we move on in the course, and that's why I do this. I deal with this topic at the exact middle juncture of the course, so that we'll carry this idea throughout this course. Any architectural tweak, convolutional neural networks, and you might have heard these terms, right? Recurrent neural networks and all these are all adding biases onto the model by doing an architectural change. The other way to do it is to modify the loss function, as we will see now. So there are multiple ways to increase the bias of the model. We will see one or two ways in this particular course. Okay. So any technique that is used to increase the bias of the model. See, when I say bias, you should know what I am talking about. It's that exact term, that expectation of HD minus that exact term is what I am saying by bias. So now it's not an English term, right? It has a precise mathematical definition. So anything that we use, that any technique that we use to increase the bias of the hypothesis is known to as regularization. Okay. Right. So now let us look at a couple of ways to do that. So multiple ways. One is called so parameter penalty is one way to do it. You'll see that, or architectural choices or restrictions. And you can also impose bias by changing the way you optimize. So optimization changes. We will see examples for all these, okay, as we move on. So let us look at the parameter penalty way of doing it. So regularization through parameter penalty. Okay. So what is ERM? So recall that ERM is that you find a function h star f of x as the minimizer of the empirical risk. So choose some loss function, and this is h of x comma y. Yeah, this is, and we do this over class of h. This is what our ERM is, right? Now regularized ERM so let me write this function as h theta of x, because these are parameterized with some parameter theta, right? Define a function uh, omega of theta, which is a function from the parameter space to r plus typically, okay, and this is called the regularizer. And define a new objective as follows. Call it regularized ERM. So find h star of x as the minimizer of the same regularized risk So now instead of solving an unconstrained optimization problem, you solve a constrained optimization problem, right? So subject to this function, okay. You can have any kind of regularizer. This is one way to regularize where k is some positive number, right? So now this is the problem that you right now solve. So instead of saying that solve ERM, you say that you solve ERM with a constraint that this particular function is bounded. Now there are two questions here. One, how do you choose this function? Actually three. One, how do you choose this function? The second question is that how do you solve this constraint optimization problem? The third question is why would this increase the bias? Okay, let's look at all of them. Now the first thing is, let's see how to solve this. Okay, to solve, so you all know how to solve a constraint optimization problem. How do you do that? Change the constraint optimization problem into an unconstrained optimization problem by defining what is called as a Lagrangian, right? So the Lagrangian, L is already taken alphabets. The function of theta, n is for, okay, I will write r cap r, r cap for capital R cap for empirical risk, and the subscript is to denote that it is regularized. Okay, so this is 1 by n So what is Lagrangian? So you have some lambda times minus k. Solve this problem. So this optimization problem, so now your theta star is the minimizer, or rather I can also say h theta star is the minimizer over theta, minimize the regularized risk. Now people have done optimization theory know that if you want to solve a constrained optimization problem, you construct you construct a Lagrangian and you solve two optimization problems, right? One is the primal and the other is the dual. This is the primal, and dual will be an optimization problem on the Lagrange multiplier lambda, right? But typically in ML community, it's not solved that way. So this lambda is assumed to be a hyperparameter and it is fixed using the validation data. So you don't solve the primal dual problem. Now you just fix it with some particular value, and by the way, in ML community, this thing is called the regularization constant. It's called the regularization constant. Choose that as, make that a hyperparameter and use validation data to fix it. That's how it is done. Okay. Yeah. So how do you solve this optimization? I mean, how do you do it in practice? For some algorithms, this will become analytically differentiable, so that you get a solution over theta. I mean, just like we did for linear models. For some, I mean, so for most of the models, depending upon the choice for h theta, this optimization problem cannot be solved analytically. You need to resort to the numerical methods, and we have gradient descent to solve it. That's it. Okay. The update rule for the gradient descent would change with this particular function, because you need to now take a gradient with respect to omega as well. Make sense? Okay. So, this is how you solve it. Now, the question is choices for the regularizer. Which data is just solve analytically or numerically. So, nothing changes, what changes is the objective function with respect to which you are optimizing would change if you add a regularizer. Okay, that is it. Now, the next question is what choices should we have to make on this. Now, later part of the class I will show you that this is precisely equivalent to getting a Bayesian estimate. Now, this question of what choice should we have to do for regularizer is exactly the same as what choice should we have to make for the prior that we choose on the parameters. So, I have been telling that the prior that we choose is a user defined parameter, and that is why it is called bias, right. Whatever choice you make, but the thumb rule is to make a choice such that the choice on the prior that we have made is meaningful. In what sense? That, remember our example on the Bayesian estimate, right. If we are tossing a coin and we are estimating the success probability using Bayesian methods, we use the physics of the problem to constitute our prior. Can be a conjugate prior as well in the case of map, right. So, similarly, look at what problem you are solving, and depending upon the problem that you are solving, you make a choice on the regularizer function. Okay. So, there is no systematic way of doing it, in the sense that since it's a user defined choice, whatever choice we make is the choice that we have to live with, right. But and we make this choice pragmatically depending upon the physics of the problem. That is how we do it. I will give you a few examples of it. So, one way to do it is, so use this to be pth norm of parameters. Okay. So, specific cases, right, if you have this to be 2, this is called the L2 regularizer, and if you make it to be 1, it is called the L1 regularizer. It also has other names. I think this is called this is lasso, no, this is ridge. So, one is called lasso, the other is called ridge. I keep forgetting which is what. Come again? This is lasso, this is ridge. Bad at names, you know. That's why I keep saying no, L1, L2 is better. L2 for 2 norm, L1 for 1 norm. Right? Okay. So, you use norm penalties, right, on the parameters, and that is one choice to that. There is no reason why this has to be the norm, it can be anything else. So, this is one way to do it. Now, why is this choice made? What is the rationale for this? This typically comes from the polynomial regression community. See, remember in our example, the two hypotheses that we chose, one was the one that was oblivious to data, the other was a lookup table. I also told you that if you have 10 points and you are looking at a polynomial generalized linear regression, you can have a 10th degree polynomial and then you can get 100% accuracy. Now, suppose you regularize the 2 norm of this polynomial regressor. How many parameters does a polynomial regressor will have? 10th degree polynomial regressor will have 10 parameters, right? 10 or 11, I mean if you count the constant as well. So, this is a 11 dimensional or 10 dimensional vector. Now, what am I saying by putting this penalty here is I am saying not only reduce the empirical risk, but also ensure that you choose the parameters in such a way that the norm, okay, of this parameter, of the parameter vector, mind you, the norm of the parameter vector is reduced. You see what I am saying? What would the regularizer do? Okay, regularizer would say that along with minimizing the empirical risk, you should also minimize the norm of the parameter vector. Okay. Now, think about it. What would be the minimizer for a 10 dimensional vector? What is the minimum value of a norm of a 10 dimensional vector? All zeros. Okay. So, the optimizer would gravitate towards making all parameters 0, but it can't do that. Why? because the other objective, which is minimizing the empirical risk, has to ensure that the loss that we have observed on each of the data points that we have also has to be minimized. So, it cannot gravitate towards making all parameters 0. Now, what would it go to is the question. Yeah, some of them will be made 0 or some of them will be made smaller. Which ones will be made smaller? The ones, why? I mean, it depends upon what your underlying distribution is. If your underlying distribution, in the case that we took, right, I constructed a distribution by perturbing a parabola, you see, which is that it is perturbed over a second degree polynomial. In that case, if this optimizer has to minimize both the objectives, okay, especially the empirical risk, it has to make sure that the higher order terms are put to 0 or the coefficients corresponding to the higher order terms are put to 0. Otherwise, if the underlying reality is close to low frequency or lower degree polynomials, then you cannot bring the empirical risk lower by putting the lower degree terms or the coefficients corresponding to the lower degree terms towards 0. You see this? So, this is how regularizer works. Okay, putting a norm penalty. So, now you see, for those problems in which the reality is mostly low frequency, parameter norm penalty works well. Make sense? Okay, I mean, you understand what low frequency means, right? I mean, in images, what is low frequency? If you have lot of pixel noises, etc., sharp edges, they are high frequency. If you have smoother images, they are low frequency. Again, one can make an assumption that most of the data that we get are typically low frequency, and that way norm penalty works as a good regularizer. Do you see how it works? Yeah. So, norm penalty is one way to do that for the regularizer. The other way other choices can be, see, as long as it is a function that you are choosing, one can choose any function on this. So, you can actually make this to be some negative exponential of this, right. This can be another regularizer and so on. Again, it's a design choice. One can choose it to be anything. So, that's a possibility. Okay, so we have answered two questions, which is how to solve regularized DRM. So, what choices should we have to make for regularizer? The other question is, yeah, question. L0 is not a norm. You know that it's not a norm, do you? Right? So, okay, you can choose L0 as a choice for this, but you'll have to also ensure that the function that you have chosen is differentiable, because you are ultimately solving an optimization problem, and you will have to the numerical differentiator or whatever, right, has to ensure that it is differentiable, and L0 is not differentiable. But of course, if you can take some subgradients or something and manage with it, L0 norm is fine. Yeah. Okay, we will stop here and continue in the next lecture.